Okay, introduction to logarithms. So let's take a look at the exponential equation, like y equals 2 to the x. So if you put in 0 for x, if you put in 0, you get 1. If you put in 1, you get 2. If you put in 2, you get 4. Put in 3. 2 to the third is 8. 2 times 2 times 2 is 8. And if you put in minus 1, you get 2 to the minus 1, which means 1 over 2 to the 1, so that's 1/2. Minus 2, you'd put in 2 to the minus 2 is 1/2. The negative makes the reciprocal the base to the 2, so that's 1/2 times 1/2, which is 1/4. And similarly to the minus 3 is 1/8, and so on. So if I make a graph of this data, 2 to the x, or of that equation, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is up about here at 8. To the minus 1 is 1/2. 2 to the minus 2 is 1/4. 2 to the minus 3 is 1/8. In this graph, characteristics of this graph, its domain it exists for all values of x. You can put any number in for x and you'll get a y value. So the domain is all reals. The interesting part is the range, which it only gets closer and closer and closer to 0, but never hits 0 and up. So it's from not 0, but to infinity. Now let's do this graph's inverse. So now I'm going to graph, instead of this being x and this being y, the inverse is the other way around. So I'm going to put in 1 is going to be 0, 1, 0, x, y. I'm doing it the other way around. 2 for the x, 1 for the y. 2 for the x, 1 for the y. 4 for the x, 2 for the y. 4 for the x, 2 for the y. And 8, 4, 5, 6, 7, 8 for the x, 3 for the y. And 1/2 for the x minus 1. 1/4 minus 2. And 1/8 minus 3. And as we learned before, the inverse is a reflection over the y equal x, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. It's a reflection over this line. This is a mirror image over that line. So what's the equation of this? So let's solve for x in this. So instead of y equal 2 to the x, to find the inverse, remember back when we did these before, we changed the x's to y's and the y's to x's. So I go x equals 2 to the y. Now, how do you solve for the y? We can't do we could do 1 over y, but that doesn't get y by itself. That just makes x to the 1 over y. We can't subtract 2 because this is y to the 2. There's no way to do it. In fact, a gentleman from France, Mr. Napier, was looking at these, and he's not sure what he should do. And so he made up something. Just like mathematicians made up the square root of -1 is I, he made up, to what power do I take 2 to get x? And the answer was y. According to this, 2 to the y is x. So he just made this thing up called a logarithm that says, basically, begs the question, to what power do I take, and the base. Now this is called the base of an exponential. This is called the base of a logarithm. It's log subscripted, written down lower than the regular line. Here's the line of the writing, and this is subscripted. Do I take 2 in this case to get? So all these English words that I wrote here is what this encapsulated. That's what log means. To get x. And the answer to this question, to what power do I take 2 to get x? And the answer is y. This, if I were to graph this, looks like this. So let's take a look and see how we do that. So if I come to a calculator or Desmos, I can type in y equals 2 to the x. And if I go zoom 4, we can see that it looks like what I drew here. Not as much. It only goes up to 4, so it only gets to that far. Now, how do I type in log base 2 of x? So on the calculator, there's a button called log, but that one's base 10. And there's ln, which is log base e. We don't want to use either one of those. So in my math button, there happens to be a log base button. And on this calculator, it allows you to type in the base as 2 and x. Now, I just put this on the wrong screen, so I want to put it into y equals. So I come down here and go, there's log base 2 of x. And let's see what the graph looks like. This one will be in red, just like I was in red here. And graph. And it looks like this one. All it is the inverse of 2 to the x. Log base 2 of x. Okay? So, what is the domain for the log base 2 of x? Well, the domain of this thing is from 0 to infinity, not including 0. And that's an important feature that I want to get you to realize. Logarithms never you never can take the log of a negative value. Logs only exist in the positive world. There's no logs of negatives, at least for this course. No logs of negatives. The range, however, on this is like this. It goes from negative infinity all the way up to positive infinity. It's all reals. So we're switching the y and x to get the logarithm equation, and the domain and range swap. Okay, so this is an important thing. You can't take logs of negatives. Okay. Now, why is this at all important? Let's now go back to something we were doing on the last unit, like 1/8 times 4 to the 2x plus 1 equals maybe 2 to the x. And we looked at this and said, if we can make these all be the same base, we could solve this. Well, 1/8 was 2 to the negative 3. 4 is 2 squared, and that was to the 2x plus 1. And this is already base 2 to the x. Then we used our rules about powers, which was if we have a base to a power, we multiply them. So we get 2 to the negative 3, let's leave that alone, and we get 2 to the 4x plus 2 equals 2 to the x. And then if we're multiplying with the same base, we add the powers, so we get 2 to the 4x minus 3 plus 2 is minus 1 equals 2 to the x. Same base, so the powers must be the same. So 4x minus 1 has to equal x. If I subtract 4x from both sides, I get minus 1 equals minus 3x, and divide by negative 3, and x equals 1/3. And that's what would make these equal. Now, what's this got to do with logs? Okay, so we're going to do a little bit of log stuff here, and then I'm going to work into a problem like this. So hold on to what happened here, and now I'm going to ask you, so to what power do we take 2 to get 8? Well, 2 to the third. 2 times 2 times 2. 2 to the third makes 8. Do you understand that? So I could ask, to what power do I take 10 to get, say, 100? And well, 10 to the 2. 10 squared is 100. I could say, to what power do I take 1/3 to get 9? Well, I need to turn the 1/3 over, so I'll put a negative power on it. That'll turn it to a 3, and then square it, and that would make 9. 1/3 to the negative 2 is 9. To what power would I take 10 to get 0.01, which is 1/100th? Well, I'd have to take negative to make 10 into 1/10, and then to the 2. So those are some common logs, some easy ones to do. The one I want you to understand that's related to this is, so what is, let's say, 2 to the log base 2 of 8? Now, up here, we decided the power we take 2 to get 8 is 3, so this is the same as 2 to the third, which is 8. Or I could say, if I take 10 to the power, to what power do I take 10 to get 100? Well, that was 2. So this is 10 to the 2, which is 100. Or I could say, let's do this. 1/3 to the power log 1/3 of 9. Well, we decided this was negative 2, so I'm taking 1/3 to the negative 2. The negative turns this into a 3, over 1 instead of 1 over 3. And then squared, it becomes 9. And what I'm hoping you're seeing here is if I have a base and a log to the same base, these pretty much just cancel each other out and become just this number. So 10 log base 10 of to the power log base 10 of 100 is just 10 squared, or 100. It just becomes this. Base and the base are the same, so this becomes 9. Which means I have this kind of rule now that if I have some base log to that same base of a different number, that's just a. Or another way to write a. Just like when we were learning fractions, we learned that we can write 1 many ways. We can write it as 2 over 2, or 3 over 3, or 4 over 4. Well, we can write a as b to log base b of a. So, back to this kind of problem. If I have a problem like, say 5 times 3 to the x plus 1 equals 7 to the x minus 2, there's no common base between these three numbers, like there was on this. 8 was some power of 2, 4 is some power of 2, and 2 is 2. There's no common base. But we can use what we know about logs to write this as a common base. And I can choose any base I want. Now, the calculator happens to have log base 10 on it. Let me show you what I mean. If I type in log 7, this is saying, to what power did I take? There's no base shown, so it's on a log. If there's no base shown, it's understood to be 10. So this is asking, to what power do I take 10 to get 7? Now, if I take 10 to that power, I will get 7. So I'm going to use base 10. I could use base e, and I'll show you that in a sec here, but 5 is 10 to the log 5. Let me show you that for sure. 10 to the log of 5 is 5. So I can just write 5 as base 10 with log 5 times 3 is 10 to the log 3. And that was to the x plus 1. And 7 is 10 to the log 7, log base 10, 10, 10, so this would cancel, to the x minus 2. Now, if we use our power rules, we got 10 to a power to a power. So we've got to multiply these. And because this could look like log of, if I multiply these, log of 3x plus 1, we tend to write this in front of the log. So we write, but we're supposed to be taking log base 10 of 3, that times x plus 1. And that's what 10 is to here. And we have 10 to the log 5 for this equals, and we got 10 to the log of 7 times x minus 2. Now to work this out, I need to distribute this to both of these. I need to distribute this to both parts of this. And then I need to add this to this. So I get log base 10 of 3, understood base 10, times x. Now if I put it here, it looks like log of 3x, so I put the x in front. And then I have plus log base 3 times 1 plus log of 5, because when you're multiplying, you add this to this, and that would be the power of 10 on this side, and the power of 10 on this side would be x times log 7, and log 7 times a minus 2, so minus 2 log 7. Now, this looks ugly, but just remember, the log of 3 is just a number. Let's find out what it is. Log of 3. It's 0.477. So we have 0.477x plus 0.477 plus, let's see, what was the log of 5? It is 0.699. Now, you realize that I'm rounding these off, so these are not, I'm not going to get an exact answer, but I'm getting an approximate answer. Equals, what's the log of 7? We did that earlier, forgot it. It's 0.845. So we have 0.845 log of 7 times x minus 2 times the log of 7. So times 2 is 1.690. 1.690. So I took negative 2 times the log of that and got this negative. This hopefully looks like an Algebra 1 problem to you, where we got x's on both sides of an equal sign. We have to get them together. It just happens to be ugly looking numbers times the x's. So I'm going to collect my x's over here because this is a bigger one and I'll have positive. So I'm going to subtract 0.477x from both sides. So I end up with 0.845 minus 0.477. I end up with 0.368 x's. 0.368 x's on this side. These are gone. And now I'm going to add this to both sides to get this out of here and combine it with these. So I'm going to have 0.477 plus 0.699 plus 1.690, and I get 2.866. And I'm going to have to divide by 0.368. And I find that x is 7.788. Now, on the calculator, I've got a few extra digits here, but I was rounding a lot up here. So this answer might not be perfect, but I'm going to store it in x. I think I've showed you that before. Store that in x. And then now my calculator thinks x is that number. And that number should be what makes this side equal to this. So I'm going to type this in. And it's thinking x is this, so I can use x. I don't have to use this ugly number, sorry. It thinks x is this, so I'm going to come back up here and I'm going to type it into this. So I'm going to write 5 times 3 to the parenthesis x, it knows x, what x is, plus 1. And this side comes out to be 77,970-ish. Let's see what the other side comes out to be. 7 to the x minus 2. It comes out to be pretty close. Now, I did a lot of rounding, so we're a little bit off, but it's close. So this is fairly close to the correct answer. Okay? I would have to keep more decimal places all the way through this, or leave it with the logs all in it. And we're going to learn about how to simplify this using some log rules to get a more exact answer. But we got the decimal approximation. So, what do we know? We know, first of all, we can change, we can write any number in a base with, if we just use the base to the log with the same base of that number is another way to write a number. We know that if we have, as you can see here, if we have log of some base b of a equals c, that's kind of like 2 to the third equals 8. We can rewrite this as a power equation, b to the c equals a. So these are two things I want you to understand, and how this allows us to do this kind of problem with not common factor bases like this was. How we can move forward. The next thing we're going to do is to actually use this on some equations to solve equations, and we're going to learn a few more log rules, which are nothing more than power rules. So if you know your power rules, you will know your log rules.